Good afternoon. Thanks everybody for joining us in our symposium on collaborative animal movement studies. And in the spirit of collaboration and coordination, Julia and I actually coordinated our outfits. Totally planned it, so just to set the theme a little bit. So I'm Pam Loring. I work with the US Fish and Wildlife Service, and I'll have the first talk on a collaborative project to develop guidance for an offshore Motus network.
Sorry, these got closed. Give me 1 second. Get them all open, and then we'll go. All right.
Great, thank you. So today I'll present a brief overview of a project funded by NYSERDA to develop guidance and tools for offshore Motus projects. This is a 2-year effort that began in 2020 and is currently in the final stages. And as we get started, I'd like to thank the project team from the US Fish and Wildlife Service, Biodiversity Research Institute, the University of Rhode Island, and Birds Canada. And special thanks to NYSERDA for funding this work and making it possible. So the overall project goal is to develop standardized protocols for using automated radio telemetry to monitor birds and bats in offshore environments. Automated radio telemetry is a technology that uses radio tags and receiving stations to track wildlife. The Motus Wildlife Tracking System is an international automated radio telemetry network that is managed by Birds Canada, a nonprofit organization. Motus serves as a central data hub for collaborating projects on shared radio frequencies, including thousands of receiving stations and tagged animals representing hundreds of species worldwide. So this system of coordinated stations, tags, and data makes it possible to track large sample sizes of animals at local to migratory scales. The map on the left shows locations of Motus stations in North America, and the map on the right shows movement data from hundreds of shorebirds tracked with Motus over the last several years. And the lines on the map represent interpolated tracks between stations where birds were detected. And you can see from the map that there's extensive coverage by stations in some coastal areas, but coverage offshore is lacking, so interpolations have a lot of underlying uncertainty, especially in offshore environments. And by strategically deploying stations in offshore areas, we can increase coverage to detect animals passing through wind project areas and other sites of interest, and add valuable information to improve the accuracy of tracking data at regional scales. So for offshore wind energy applications, some of the information gaps that Motus can help address include the presence of species in offshore areas relative to covariate information, including demographic, temporal, and atmospheric data, spatial and temporal variability within and across sites, cumulative exposure of tagged animals to multiple wind project areas throughout the US Atlantic, the proportion of tagged individuals using offshore versus coastal migration routes, and geographic variation in migration routes, including departure points along the coast where animals might begin flights over open water. However, effectively addressing these information gaps depends on sufficient numbers of tags and stations deployed in the system, so a strategic approach is needed for using Motus offshore. To help meet this need, our project team developed a series of interrelated products to guide and inform the deployment of Motus in relation to offshore wind energy development in the US Atlantic. The overall project includes the following components: a guidance document with specifications and workflows for offshore Motus stations, an online study design tool that allows users to map detection coverage from stations, a simulation study to model animal movement through offshore arrays, a Motus data framework including a centralized portal for data management, coordination, and summary reports, and a monitoring framework to help guide tagging efforts and study design for offshore Motus projects. So the guidance document includes technical specifications and detailed workflows for setting up, calibrating, and maintaining stations on offshore turbines and buoys. It also includes supplementary field data sheets to help station operators record metadata in a standardized way for easy entry into Motus. The document was developed with a cross-sector project advisory committee and informed by fieldwork at Block Island Wind Farm in partnership with Ørsted and in coordination with several monitoring buoys throughout the Atlantic. And just wanted to say special thanks to everyone who contributed, including many people and organizations that are represented here today. So this slide shows some photos from the fieldwork that we conducted at Block Island, where we set up 2 Motus stations on the south side of the island, overlooking the wind farm, and worked with Ørsted to deploy a station on the easternmost turbine in their array. We conducted calibration surveys by flying test tags and a high-resolution barometric GPS unit along transects at different altitudes. So the photos on the left show the test tag and a GPS on a kite that we flew behind our boat at altitudes up to 130 feet above sea level. And the photo on the right was taken during an aerial calibration survey flown at altitudes up to 1,500 feet above sea level. There's generally a positive relationship between tag altitude and detection range of stations, so it's important to collect calibration data across a range of flight altitudes to more fully understand station coverage for tracking different species. So this map shows detection data from one of the kite surveys. Both the test tag and the GPS were collecting data every second, so the data had very high temporal resolution. And the map shows detections of the test tag from the 2 stations on Block Island and the station on the turbine, which is shown in blue in the track line. 96% of all tag pings were detected during the survey by at least one of the 3 Block Island stations, and we had some additional detections from stations on eastern Long Island that were located 30 to 50 kilometers away. Our collaborators from the University of Rhode Island, Eric Carlson and Doug Gobet, used data from these surveys to develop antenna beam models to estimate 3-dimensional coverage of the tracking stations. And Andrew Gilbert at Biodiversity Research Institute incorporated the antenna beam models into an online study design tool called IDIOMS, which stands for Informing the Design and Implementation of Offshore Motus Systems. The tool is available as an R-Shiny app and helps users optimize numbers and locations of Motus stations within a lease area by mapping estimated coverage from the antenna beams. It also allows users to simulate seabird and shorebird tracks to estimate proportion of individuals detected. And Evan Adams from BRI led the simulation study, and we'll discuss that in detail during the next presentation in this session. Results from the tool are summarized in automated reports that contain key information on study design that can be included as standardized elements in post-construction monitoring plans. In addition, project co-leads from Birds Canada developed a data framework within Motus to coordinate information among offshore Motus projects. The data framework established an Atlantic offshore wind group within Motus that includes an online interface for data exploration and dynamic summaries of station and tag data. We also developed a process for automated report generation to provide standardized, transparent, and timely information within and across sites. And the framework outlines a process to efficiently coordinate access to detailed detection data and metadata across projects for use in offshore wind research, assessments, and monitoring. Lastly, we developed a monitoring framework that provides a roadmap to design and implement offshore Motus studies. Specific objectives of the monitoring framework are to standardize methods for site-specific monitoring and reporting, coordinate information across sites for regional scale analyses, develop a centralized tag deployment strategies to inform population-level inferences from individual-based tracking data, identify standardized data analysis methods to address high-priority information needs, facilitate regional coordination opportunities to maximize resources, and recommend high-priority future actions identified during framework development including improved workflows, analysis tools, and integration with other bird and bat monitoring technologies. The final products will be released in fall of 2022 through the project website hosted by BRI and through a dedicated page on motus.org. And the products are intended to be living documents that are updated as new information and technology becomes available. So stay tuned for the official release and an informational webinar that we'll be hosting this fall along with the release. And with that, I'd like to say thanks to everyone for being here today and to thank all of you who were involved in this research and effort over the last 2 years. And please feel free to reach out with any questions or if you'd like to coordinate efforts moving forward. And next up, we have Evan Adams, who will be talking about study design choices for offshore Motus.
Thank you. All right. Thanks, everyone. And thanks, Pam, for that excellent introduction. For people at home, you need to keep track of how many times you see the photo of this piping plover. Okay, so we're going to talk a little bit more detail about the simulation study and the study design assessment that Pam was just mentioning. But just for some completeness, this is a product of the Atlantic Offshore Wind Assessment Collaborative. This is the group that Pam just mentioned with BRI, Birds Canada, University of Rhode Island, Fish and Wildlife Service. And this has been funded by NYSERDA. And hopefully we're going to be continuing this with actually Project WOW and the DOE-funded work that we're going to be doing in the coming years. So, as Pam was just mentioning, well, as we are trying to understand the effects of offshore wind on seabirds and shorebirds in these areas, we have often not as many choices as we would like. There's a lot of planning. There's a lot of areas of coverage for offshore wind in the northeastern United States. And there is a potential conflict with a few species that are of regulatory interest, like red knots and roseate terns. Particularly, there's areas of breeding colonies for red knots and important staging areas, breeding colonies for roseate terns and important staging areas for red knots. And so we have an opportunity here to potentially use Motus to help us fill some of these gaps. So the Motus network, I'll just do this very briefly, is a collaborative research network. It's a program that's a partnership between researchers and organizations. And teams across the hemisphere capture and tag birds which are detected by an array of towers across the world at this point. When birds are detected by a tower, the information is transferred to a database and tracks are defined. And Pam went over this already, so I'm not going to weigh on it too much. And as she also said, the coverage for Motus is doing very well on the coastal side of things. But offshore, we don't have as much information. There's a pretty significant gap. And so if we're trying to use data that we're gathering via Motus technology to inform decisions that are happening in the offshore environment, we have to do something about that to cover this. And so this is what Pam was mentioning earlier. We're providing guidance and hopefully some coordination so that we have a better way to sort of deploy these towers in these offshore systems. So, but what I'm going to be talking about today is hopefully how do we inform this process? How do we make sure that we're using our resources in the most efficient way possible and make sure that we are giving people good guidance for how to deploy these systems offshore so that we can maximize our knowledge gains. So overall, our project goals are to create clear guidance for Motus stations and offshore wind projects, provide decision support tools like idioms that Pam was mentioning for designing offshore monitoring studies. But we also want to talk about optimally deploying resources and assessing presence, absence, and also the capacity for Motus stations to estimate movement patterns. And that's what I'll be talking about today. So while we don't have a lot of offshore wind in North America, we do have a little bit, and Block Island Wind Farm is our first commercially sized project, and we were able to use it, as also Pam was mentioning, for some calibration work. So with deploying Motus stations at Block Shore Wind Farm and coastally along the island of along Block Island itself, we were able to gather a fair bit of information on how well these stations pick up Motus transmitters at a variety of heights. So as Pam was mentioning, we have water or sea-based methods where we're dragging kites behind boats, and we also had air-based methods to essentially dragging Motus tags around and getting picked up by these Motus stations. Once we do that, then we can figure out exactly how big a volume of area these Motus stations are picking up. So we can estimate this detection field using the strength. So we have the GPS on these calibration studies, and then we have a tag. And so we can tie the GPS position to the strength of the signal and which antenna we're sensing it out of. And so we built calibration volumes for both omnidirectional and omni antennas and directional antennas like Yagis. So we can have a pretty good sense of where animals should be getting picked up by Motus stations as we deploy them offshore. So, but because we don't actually have any stations, a lot of stations offshore, we need to sort of make them up more or less to try to figure out what the optimal way we can allocate resources is. So that means we have to do some simulation work. So the way the process works for this study in general is first we simulate movement tracks. Then we simulate an offshore wind array of turbines that we deploy Motus stations on, and then we use the calibration model that I just mentioned to determine how many of those movement tracks are being detected and where, and we can use that to assess a variety of different study design choices. So just to go over broadly, the movement tracks are a couple different species, different types of tracks. We used common tern data to look at non-breeding season movements of common terns. We used piping plover data to look at migratory movements of piping plovers, built some tracks based on that, and then tested it under a variety of conditions. So from a design analysis standpoint, we wanted to test three major things, and then we kind of added something else relatively recently that was interesting. So first we wanted to test this movement type, what kind of movement the animal was doing, these sort of these larger scale, like tern-like movements that are, sometimes they're flying long distances, sometimes they're foraging, versus a shorebird flying offshore, which isn't really pausing, they're just sort of going in a singular trajectory. We looked at a variety of flight heights for each of those different movement types. We varied them. For the tern-like movements, we kept them low to the ocean. For the migratory movements, we kept them, we allowed them to go higher. We tested 5 different types, deployments of Motus stations, between 1 and 6 total stations, or 7 and 40% of the total coverage of our simulated turbines. And we also tested 2 different inter-turbine distances. So essentially we spaced the Motus stations either 2 kilometers apart or 10 kilometers apart. So we tested a variety of different things that could be changing in these stations. Then on the other end of things, we wanted to know how many individuals were detected. We simulated and released a known number of individuals, so we can just tell you what proportion was detected. We can look at the number of positions that were detected, so how many times do we think they were going to be detected by these stations so you can have multiple detections per individual. And then we also looked at cumulative detection probability and the probability of being detected in 2 different antennas at once, which is really important for understanding, using these data to build movement models and actually estimate 3-dimensional positions of animals, rather than just say, we know that they were there or they were in the vicinity, but actually begin to understand their movements in these environments. So we really wanted to understand that as well. So that's the setup. We tested a bunch of different scenarios, ran a bunch of models, and then we essentially what we wanted to know is, what is the effect of increasing the amount of Motus station effort at these simulated turbines? How much more bang for your buck do you get by putting more and more Motus stations out at these locations? So first, for the seabird type movements, so to orient you here, on the x-axis is the number of Motus stations. On the y-axis is the proportional change. So how many more of the thing that's grouped at the top there that we see. And then finally, the groupings, it's the number of individuals, the number of detections, and the cumulative detection probability. And the uncertainty you're seeing is we varied the detection threshold to see how much that might matter. We were trying to get a sense of how much individual variation in like tag quality and behavior might influence that, and we had a rough approximation of how much we think that might influence signal strength, so we projected that through as well. So with seabirds, if you go to the left and look at number of individuals, you can see that we actually plateau relatively soon. We get to about 3 stations, and we find that we don't really see a whole lot more past that, probably because we're doing a pretty good job of sampling the entire project area. But if you look at the number of detections or the cumulative number of detections, we find that essentially, it only keeps going up. there's a little bit of variation in like how much it goes up exactly, but we're not really seeing a threshold, which indicates we haven't really saturated the stations yet. And that's kind of interesting to note. So more or less, if you're interested in seabirds and you want to see multi-tower detections, you can't stop sampling enough. I mean, obviously we will logistically, but it's good to know that like more stations just continue to equal more value, which is quite important. Let's see, uncertainty in the detection process, those error bars are fairly large, and so we think there's going to be a fair amount of individual variation in this, which is also interesting. And finally, flight height, which you can see in the color of the lines, didn't seem to matter that much, with the flight heights that we tested at least. For shorebirds, we see fairly similar patterns where we're seeing a similar plateau at around three stations. Of the 15 turbines that we tested this on. And then we also see similar kind of continual decreases, though there does appear to be more of a threshold perhaps where we're getting less value out of putting out more Motus stations. So effort does translate well into more positions, but it is a little bit, but it might be a little bit less one-to-one as we were seeing with seabirds. Flight height, again, doesn't seem to matter that much, which we find is interesting, and I'll talk about a little bit more later. Finally, we wanted to look at simultaneous detections. So these are the things we're going to need to estimate 3D positions as we're going down this road of trying to understand that better. And so this is the proportion of the total number of detections that were from multiple antennas or multiple towers. And we find that it actually doesn't increase that much this is across both species. We have shorebirds on the right and we have seabirds on the left. And it does increase, but like not by an extremely high margin as you increase the number of towers. This is on the 10-kilometer turbine spacing. This is probably because we are arranging these stations to be fairly, to have maximum coverage, not maximum overlap. Obviously, there is some increases, there is some value here, but we weren't seeing really high amounts of increase until we started allowing the turbines and thus the stations to be closer, and then we can see a really significant increase in the number of multi-tower detections. So putting stations very close together gives you an opportunity for a lot of coverage overlap in their detection zones, and that gives you a lot of chances for multi-tower detections, which is going to be very helpful. Notably, we saw this more with shorebirds than we saw with the seabird movements, which we find interesting. This likely has to do with how we estimated the migratory movements. So let's get to some high-level summary here. Increased effort led to increases in all the metrics we're talking about, but we definitely saw caps in the number of individuals detected. But the other features we saw less. We can continue to get a lot of detections as we put out more and more Motus stations. Flight height didn't make that much difference here. We're going to look at this more. We think we need to look at the calibration model a little bit and maybe get a little more finer in how it's treating kind of heights in the kind of the lower zones that we're measuring here. And multi-tower detections were more common with the shorebirds, and I think station proximity is going to matter a lot there. So when you're thinking about studies, there's a lot of different things. I think the important thing is the response you choose, like what you want to do, measure presence, absence, get these multi-tower detections, try to estimate 3D positions, really impacts the type of study that you want to design. So it doesn't seem like movements make as big a difference, or the type of species you're covering, as long as the species is going out to the area you're interested in. And then from there, it matters like what kind of data you want and what kind of study you want to do. And that really needs to guide how you want to set up your study. So as Pam mentioned, just for completeness, if people are watching these out of order after the fact, we have idioms, which is a study design tool that will be coming out that allows you to visualize some of these things. It doesn't let you do a full simulation study, but if you want to, talk to me. I'm happy to share code on it. We have a paper that's getting there. And we have deployment guidance, which Pam just mentioned as well. So that's all coming out relatively soon. So with that, I'd like to say if there's save questions for later, but I'm happy to answer anything you have.
Thanks, Evan. Next up, we have Andrew Gilbert, who will be talking about a SCRAM model for offshore avian collision risk.
Hi. Good afternoon, everybody. Today I'm going to be discussing a new tool that is being developed in conjunction with collaborators at BRI, Evan and Adams, Kate Williams, as well as Pamela Loring, Fish and Wildlife Service. It's basically a flavor of collision risk models that we are calling SCRAM. It's going to be an R shiny tool, and it's the main difference is that we're using movement data versus density estimates from surveys, which were used by past collision risk models. And so this is just a kind of overview shot of the tool itself. I'll get a little bit more into what the pieces are here, but like I said, unlike previous models, this is using movement data, so using the Motus tagged animals. And I won't go into Motus at all. Pam did a great job describing that. But suffice it to say, we basically are taking this Motus data for, in this case, the 3 species of listed birds found here, and creating a movement model, and that combined with population estimates allows us to estimate density. You know, we don't have good density estimates for piping plover and red knots offshore. We have some for roseate terns. So this is helpful for us to start doing these collision risk models for these species we have limited data. So I'm also not going to really get into collision risk models. There's a lot of information out there. They're somewhat complicated. You can look at various papers on that, but essentially it's an assessment, a quantitative assessment of the probability of a collision between a bird and a turbine and some measure of the total number of birds at risk over a designated time frame. So that could be a month or a year. And the basic inputs are species, physical properties of the species, and the turbines or wind farms, and those that really affect collision risk. And another difference between this model and the original models that people often refer to, the BAN 2012 model, is ours is stochastic, and so it accounts for some uncertainty, and versus original deterministic models, which were basically a point estimate, with no uncertainty. And I just wanted to put in this sort of history of where we came from. The original BAN 2000 model, or in the early 2000s, was an onshore model that was deterministic, and then he created the BAN 2012 model, which is mostly what's been used in sort of more recent past, which is another deterministic model, but focused on offshore turbines. And there's an Excel spreadsheet to do this. And then we moved into the stochastic phase of these models. Marsden created a version that uses R, and there's some R code to do it. And then from that, McGregor developed actually an R shiny tool from Marsden code and did some other fixes. And then we took that code and further adapted for movement data and built our own UI interface. So I just made this figure to kind of show the various inputs and the fact that a lot of them, both the turbine parameters have measures of standard deviation and uncertainty in them, as well as the bird parameters. And that allows us to sort of propagate this uncertainty through the model into our estimates of risk. I will note that the flight height distribution and the occupancy information are both models from the Motus data. Flight height distributions are bootstrap Monte Carlo estimates at various flight heights, and so we have uncertainty built into that. And then, and really these are Evan Adams babies, although derived from some prior work done at URI. And then the occupancy model is he told me what these, hierarchical Markov model. There we go, done. If you want to know about those specifically, you should really talk to Evan. So again, as a reminder, this is right now in version 1, although we're not actually on, quote, version 1. It's just for piping plover, roseate tern, and red knot. In order to add additional species required some more coding, and things were kind of failing. And so we sort of backed it out to what was most needed right now. But the nice thing is that all the data to run those is baked in. So and that data is outputted at the end, so you have it, you know what it is. And also further, you can look at it, and I'll show that in a little bit. So this is the main layout of SCRAM. There's a sideboard on the side for inputs. There's some tabs in the middle for looking at inputs and also outputs. And then, is this an actual laser pointer? These are hard to see, but manual GitHub site, so the code's available to look at, not yet, but it will be, and then a bug link. Oh, and I should point out, there's one button on here you may miss, but this is for downloading example wind turbine inputs, and that's the only inputs right now that you need to modify, although you don't really, because if you just want to play around with it, you can download it and then basically upload it again, which is kind of silly, but that's what happens. So stepping through this, the first thing it's going to ask you for is what's your name, what's the project. I tried to put some fields in here so that in the output, it's sort of reminding you, oh, this came from this project and this is the person who ran it. But anyway, you select the species, and then it will automatically display what the inputs were that were baked in and any of the uncertainties. And so there's some, the various species-related parameters like avoidance rate and wingspan and all that. And then it shows you on the right in the figure there, it's maybe a little hard to see, but that's the flight height model, flight height distribution model. And I put a little slider in there so you can kind of zoom in and out because there's a point for every meter, so it's kind of crowded. And then on the bottom is the population estimates, and that we worked on with Pam and her colleagues at Fish and Wildlife Service to derive these monthly estimates for the 3 species. And there's assumptions and limitations, and I make sure they're there, and then they also get reported out so you know what all those are. And then this is the stage where you enter the turbine information, and so you have that file, you modify it, you upload it, and then it shows it, so you make sure you can check all of those, you know they're right, you didn't make a mistake. It will show you where it thinks the turbine is that you just told it you uploaded, but also there's one bit of species information here. On the map at the right, it's showing the occupancy model as we have loaded up, but it's actually a mean of the occupancy model because they're actually monthly specific models for where we have months of data. And then there's one more set of model inputs. You can choose the sort of flavor of this collision risk model, and these roughly are equivalent to the band 2012 option 1 and 3. One's a faster approximation, and it assumes sort of the same or constant risk along the rotor swept zone. And then option 3 actually tries to estimate in slices basically the risk along the rotor swept zone, because we know flight height is not the same as you go up in altitude. And then model iteration, so the number of model runs or simulations you want to run, 1,000 is sort of recommended as a minimum, and it goes up to 10,000, at which point, and some prior work was done on this, it seems that you basically don't gain anything more from doing more runs. And then you can set a threshold, and this doesn't affect the model at all, it just will report out basically the proportion of model runs that exceed that threshold, yearly threshold collision risk, and then run the model or cancel it if you need to. And so moving right on to results, and again, this is just an example, don't take anything for this, but we kept the output just pretty basic here, but the output that you get in both the output results as the file output results, and then also as a report are more detailed. So, but here this is basically showing for each run, and I should say that for the wind turbine parameters, you can actually have different parameters on different rows. So you can have, say you had a 6 megawatt option and a 15. You can put those in there and run them simultaneously, not simultaneously, but at the same time, and it will output both of those. There is a tab here that will show the differences, and this is just a frequency model showing the collisions that were simulated for all those, say you did 1,000 runs. And so on the the right are 3 additional buttons. There's a run sensitivity analysis, and then there's a generate or download the model output, which includes inputs as well, and then the report that we have sort of automated. And so just a bit about sensitivity. It's really an approximation. It was a very somewhat clever way that Chris Field, who originally started working on this from URI, and we sort of inherited it, he came up with this method to do this quickly, because to do a full sensitivity analysis is quite involved, and it would never really finish very quickly in the time frame we care about. But anyway, I put this up to just say you can run this quick and dirty sensitivity analysis. It'll show you roughly how the results vary. The point is that, from prior work, we know that avoidance is a big one. There you go. And so there's download output. I've basically given you a list of all the output and inputs as well. That basically everything that went into the model, I'm having it be exportable as well, so you have a good sort of chain of custody of everything that went in and came out. And then you also have the option then to do this custom report. And this is not really how it's laid out. I did a bunch of screenshots of the PDF report, but just to show you, and that's possible to see, I think, but there's some tables of the inputs, and you get a map of the wind farm as well as the occupancy model. And if you have, there's actually multiple turbine sizes, and you'll also see multiple rows of data for each one of those. And then here's the one output table showing you the various numbers of collisions and lower and upper prediction intervals. And then some more tables saying kind of the same thing. Sorry, that was kind of quick, but eventually you get to play with this in, I don't know, probably early fall. It's kind of needs to be fully vetted still. So, thanks.
Thanks, Andrew. Next up, we have Juliet Lamb with a framework to determine optimal sample sizes and transmitter distribution for individual tracking studies.
Hello, so I'm here with our spokesplover once again. Yeah, so I kind of joined this team, kind of tag teamed with this team, I guess, to add a piece about how once you've got your Motus array in place offshore, you have to sort of think about the tag deployment piece as well. So how do you decide how many tags to deploy and sort of where and when to deploy them? So I probably don't need to go into too much detail about why individual tracking studies are important, but there are definitely multiple reasons that individual tracking is sort of key to understanding effects of offshore wind development. So one of them is describing linkages between locations and life stages. We have a lot of really good distribution models, but in many cases we don't know where those birds that are occurring offshore are coming from or where they're going. So understanding how individuals move through space and when they're moving and why they're moving and where they're going to is really key to understanding how to sort of monitor and mitigate effects at the demographic level. Individual tracking is also key to detecting presence of species that are difficult to observe directly if they're not visually observable. And to monitor effects of things like displacement and changes in habitat use, we really need individual-based tracking data to do that. However, this also requires making inferences from very small sample sizes. So even if you manage to get a lot of money, track a lot of birds, you're still dealing with a very small percentage of the overall population that you can track individually. So to make sure that the inferences are robust across the entire population, you really need to understand what your target population is and make sure that you're sampling it and that you don't have sort of biases. Because any biases that you have initially can limit the applicability of your results and skew your final results. If you're missing certain segments of the population inadvertently, if the sites that you're choosing to tag at aren't necessarily representative of the overall population, then you can be making inferences that don't necessarily apply across your entire population of interest. And Motus studies have some particular quirks relative to things like GPS tracking and satellite tracking studies, in that you're dealing with these two separate components, both the distribution of antennas across the landscape as well as the distribution of transmitters across the landscape. And correctly designing both of these components affects what individuals you're going to be detecting and where. So the results that you end up with and their sort of applicability across the population are really sensitive to both antenna array design and tagging design. You've heard a bit about antenna configuration and how some of the work that Pam and colleagues are doing is sort of informing that. But my piece is really looking at how do we figure out what appropriate sample sizes and distributions are for the transmitters that we put out on birds. So this could be a basis for sort of making funding recommendations, building in requirements for providing tags into offshore wind leases. And the sort of sample design considerations can vary by not only the species that you're interested in tracking, but also the questions that you're interested in answering. So the goals of my power analysis really were, first of all, just to figure out the number of tagged individuals required to represent population level occupancy patterns. And I'm just looking at occupancy here, nothing more complex than that. So I'll get into that a bit later. And then looking also at the number of tagging sites and years that are required to maximize detection of birds on the landscape at sites that they're occupying. And then finally, to look at how the layout of receiving stations relative to tagging sites affects the probability that birds will be detected in given different locations, given that they're present there. So again, I'm working with previous data collected by Pam as part of her BOEM-funded research primarily, so focusing on two main species, piping plover and common tern. So there are several key differences between these species that sort of affect their movement patterns and their detectability. So the piping plover is a shorebird, and it's a sort of relatively solitary, relatively dispersed across the landscape, whereas common terns, which are seabirds, are fairly gregarious. So both during breeding, when they're colonial breeders, and then outside the breeding season, when they forage in large flocks, they're pretty social. Piping plovers nest on beaches, again, relatively spread out, while common terns are nesting in these offshore colonies in relatively dense aggregations. And piping plovers tend to migrate fairly close to the coastline, while common terns can migrate up to 50 kilometers offshore. So for piping plover tagging, the main locations were sort of three different locations. We have two locations in sort of Massachusetts, Rhode Island, one along Monomoy Island, and one kind of along the Rhode Island coast, which I grouped together into a single location for the purpose of this analysis. And then we also have 1 year of tracking from birds in the Bahamas. And then common terns, we have three different locations. The Monomoy, again, pretty similar to the piping plovers, some locations in Buzzards Bay, Massachusetts, and then also Great Gull Island. And so I conducted a bootstrapping analysis. So basically what this involves is setting up kind of each of the used antennas, relating those to the birds that are detected at those antennas, and then gradually changing the number of birds that are included in the sample. So you start out with one bird. Those can be any bird that's selected at random from the group. Then you start selecting 2 birds at random, 3 birds at random, until you've basically are up to the full sample size, and seeing how the number of antennas that the birds are detected at changes as you increase the sample size. And what you get is this curve. So you have sample size on the x-axis and inclusion value on the y-axis. That's the percentage of used towers that are included in the subsample that you've selected. And you can see how the number of used antennas included in the sample increases as you increase the sample size. And then you can look at what number of birds you need to get to different values of inclusion. So for example, in this hypothetical example, you need about 35 birds to get to 80% of the used towers included in the sample. To get to 90%, you need to sort of get to about 65 birds, and then about 110 birds to get to 95%. So what you can see already from this pattern, and this is basically the pattern that we saw across all of the sites and species, is that the marginal value of including more individuals tends to kind of increase very quickly at the beginning and then start to plateau. So you need more and more individuals to get incrementally better inclusion values for used sites. And the difference between the final inclusion value and 1, so full inclusion of all the sites, I called the representativeness value. So if you're taking a single site out of multiple sites, how well does that site represent what the full population is doing? And when I say population, I'm obviously referring to just the sampled sites, not sort of the entire population of the species. So looking at just if you took a single site and sampled at it, what kind of values do you get? We found that for a single site, you needed about 40 individuals, and it varied by species, fewer terns and more plovers, to detect 80% of the used tower sites. To get to 90%, you needed maybe around 80 individuals on average, but that distinction between plovers and terns became really more apparent with much higher sample sizes needed for plovers relative to terns. And then the representativeness values of single sites really varied a lot, both within and between species. So depending on what site you chose, you might get more or less representative values for the entire population. When you looked at the overall population for each species, you need about 90 to 145 individuals to detect 90% of used sites, for example, if that's kind of a target value. We found actually that there are higher rates of non-detection for piping plovers versus common terns. So about 20% of the piping plovers that were tagged were never detected by any antenna versus only about 2% of common terns. So common terns being very strongly grouped on the landscape, it's easier to kind of tailor an antenna network to detect them really well versus piping plovers being more spread out. You kind of have to be a bit more opportunistic. And there were some drop transmitters with piping plovers as well. So if you incorporate that level of non-detection of piping plovers, the sample sizes actually become a lot more similar. So it's kind of over 100 individuals for both species. So it's really important to think about these non-detection rates and factor those into sample sizes that you're tagging, so to add some kind of buffer for expected non-detections. Looking at how tags were distributed in space and time. So for a single site within a single year, we found that like a common terns had greater representation values basically compared to piping plovers. So a single site could represent the overall population of common terns better. But across the full sample, when you include all sites in all years, we had higher representation values with lower sample sizes for piping plovers. That's an interesting pattern. And then with piping plovers, we really found that adding an additional site dramatically improved inclusion values as well as adding additional years. And so, within each site, 1 year was less representative than 2, and that was less representative than 3. For common terns, there was a lot more overlap. So really adding multiple sites and years didn't make quite as much of a difference to inclusion values with terns. And then, so these are kind of illustrations of that concept. So you can see that piping plovers in blue, if you add a second site, you get a really big bump in terms of inclusion values. For common terns in red, you get a much smaller bump. And actually, the values for piping plovers of adding a site were greater in terms of improvement than adding a year. So really distributing these transmitters across space was the most important thing for them. Common terns for both sites and years, we saw limited improvements. And then adding a second year for both species resulted in greater improvement than adding a third year. We also looked at duration of transmission, so how long birds were detected. For common terns, we didn't really see an effect. The overall duration of transmission was shorter, and basically it didn't matter how many days it transmitted. Piping plovers, we saw a positive effect with longer duration. So this is a result of having different migration strategies, really. The common terns migrating offshore, basically as soon as they left on migration, they weren't detected anymore, versus piping plovers migrating along the coast were detected by the coastal array. So common terns were basically non-detections resulted from signal loss, versus piping plovers, they resulted more from transmitter loss. Finally, we looked at station characteristics, and we found a nonlinear effect. So basically, there's stations along the coast. The distance from the tagging site kind of varied, but sites that were used as stopover sites were detected more in the samples at lower sample sizes compared to sites that were less used. If more than 10% of the sample was present at any given station, it was pretty likely to be included, and the number of antennas had a positive effect on the detection probabilities. So just to conclude, we found for both species you need probably between 100 and 150 individuals to represent the site use of this regional population that we kind of predefined. But your actual sample needs might be higher, so if you're looking at species with really large geographic ranges, if you're looking at species with high migratory connectivity where different portions of the population use different breeding and non-breeding sites and are pretty close together, species that are really clumped on the landscape, and for more complex research questions where you need multiple detections, you may need larger sample sizes than what we're looking at. It looks like prioritizing multi-site studies, potentially over multi-year studies, is really key. Especially for dispersed species that you can't really characterize very well from a single site in a year. You kind of get diminishing returns after 2 years, but you still do get improvements. So multi-year studies are also important, even if site improvements are greater. And you need to really account for things like transmission duration and the layout of your antenna network when you're thinking about sample sizes. So sorry that was pretty quick, but if you have any additional follow-up questions, you can always email me and ask them during the discussion at the end of this. Thank you very much.
Thanks, Juliet. And our last speaker in this session is Rafael Hafredo. Oh, great. Who will be presenting on combining satellite telemetry data across studies for terns relative to offshore wind.
Hello, good afternoon. I'm Rafael Revoredo from Siman, an environmental NGO in Brazil. And as Pam just said, I will be presenting the combining satellite telemetry data across the studies for sterna terns relative offshore wind energy in Brazil. The data that I will show you results from efforts from the US Fish and Wildlife Service with Siman, Mass Audubon, and other institutions. As you already noted, I'm not a native English speaker, but I will try to be clear, and I will be available for any questions or clarifications. So first of all, we need to take the bird. We need to know the bird species that we were objecting in these studies that we are talking about. The tagged species are common terns, Sterna irundu and rosea tern, Sterna dugali. Both species are medium-sized seabirds that breed in the northeast US and Canada and migrate to South America during the non-breeding period, especially across the Atlantic continental shelf. It's also important to highlight that rosea tern species is endangered in US and Canada and vulnerable in Brazil. So how combining satellite telemetry data across different studies for these species was important to understanding the relation between offshore wind areas and terns. Analyzing the map that you already know very well, the offshore wind development is planned throughout the migratory range of this species. In US, some of this area are especially close to breeding sites in the northeastern. Okay. The same thing happens in Brazil. We've planned concentrate areas in northeast and south, the main roosting areas during the non-breeding period. And the involved risks include collision, habitat alteration, and displacement, which affect not just the offshore environment, but also onshore. So the first study that brought a fine-scale overlapping of the migratory flyways with the offshore planet areas was developed in US with 5 common terns tagged on a breeding island in Maine. The birds were tracked throughout the annual cycle, showing the path that was traveled from the USA to Argentina. And the fact that offshore wind energy planted areas are overlapping this path is already a hazard to these species, but the risk could be even higher for individuals that roost and feed inside of that areas. At this point, the second study that we are bringing took place in Brazil, and it was focused in roseate terns. 13 roseate terns and 3 common terns were tagged in Galinhos in the Rio Grande do Norte state in Brazil. And these individuals migrate to Galinhos, especially from the US northeastern population. And 3 of the 13 tagged roseate terns already had US bands. So the tracking of these birds revealed an intense overlap on feeding areas with the planned offshore wind energy in Rio Grande do Norte state, heading on north coast of Brazil. We can see in these images the lines of the trajectory of the birds, just overlapping with all these planned offshore wind areas. So the satellite telemetry also highlighted current risks, non-breeding areas overlapping with salt ponds, shrimp farms, onshore wind energy, transmission power lines, and oil production and exploration. And this study was especially developed inside of a major project about roseate terns mortality in power lines. So let me share a part of this project with you. Collided terns had begun to be found during a beach monitoring in Galinhos in a distribution power line that crosses the beach between 2 urban areas in the municipality. So these 2 pink areas are the urban areas in the peninsula-shaped municipality. We have the blue line representing the power line, and each red pin represents 1 collided tern. The number of collided terns started to increase in 2014 after the installation of an onshore wind farm nearby. So yeah, this amount of pink symbolizes the onshore wind farm that we already have in operation at the area. And this changed the area, showed wind farm associated with other habitat losses could affect the bird behavior and turn low-risk sites into high-risk sites. So these studies already result in some accomplishments. We carry out an international effort and collaboration to propose mitigation and solutions. In the power line case, we already installed markers to reduce or eliminate the collisions, and we are monitoring the power line to verify their effectiveness. However, the tracking studies revealed a lot of other concerns, such as the overlapping with the non-breeding sites with planned offshore wind energy areas, oil production areas, and other power lines. And here's some pictures showing in the first one, the installed markers in the beach power line. The second one, a local tern species flying with a fish in the beak, with the onshore wind turbines as backgrounds. And in the third one, terns using an oil platform to rest while they are fishing. So having said that, when we are talking about impacts on migratory species, it's important to collaborate on the studies across the migratory range, and tracking data is powerful to assess risk at a local to range wide scale. Thus, sharing individual tracking data across the studies enable better population level inferences. As recommendations, we suggest the establishment of international working groups to share information and identify gaps, as well the development of international conservation planning efforts. In this way, a multi-sector partnership is very important, especially to develop strategic designs for monitoring and risk assessment. And a great way to execute these connections and share information is to centralize data in platforms as MovieBank and Motus. And considering and encouraging the development and use of decision support tools for risk assessment, it's also a great initiative. We also highlighted some priority research and monitoring that could be implemented, such as additional tracking studies on bird movements relative to existing and planned energy infrastructure and other risks. The application of technologies such as visual and thermal cameras to document bird behavior around high-risk areas, the expansion of power line and wind farms monitoring, the analysis of bird habitat and use of areas when planning power infrastructure, and supporting efforts to create high-importance bird sites such as BirdLife International effort to establish the research sites in Galinhos at this moment. So thank you so much for your attention.
That was great. I'd just like to thank all of our speakers and welcome them up to the stage for the Q&A. If you have questions, you can either write them on the index cards at the tables, and folks will come by and pick them up, or you can submit them through the app. Testing. All right, thanks everyone. So first question is for Rafael. What is the difference between vulnerable and endangered?
Okay. Yeah, great question. So, and the levels of species that are in some way endangered, like there's that exists the possibility to be extinct. There's different levels, and vulnerable level it's under of endangered level. So these species are not so prioritized now in Brazil as they are in US and Canada. So we are doing some efforts to increase the level of risk that these species are involved. It's basically like that.
Thanks. And one more. What distance from shore is the closest point for offshore wind in the Brazil planning areas?
Oh, yeah. The offshore winds planted areas in Brazil are pretty close from the coast. Between 2 kilometers and 5, and the maximum distance is 10 kilometers, not more than that. So it's pretty close. It's like you can see directly from the beach if the turbines will be installed.
Yeah, wow, that's quite close. Question from the app for Juliet. The definition of a site for common terms seems relatively obvious, site equals colony. How did you define a site for plovers, and how might the way site is defined for this species influence your results?
Yeah, that's definitely a good question. In this case, the sites were obviously a lot more diffuse for piping plovers, so these were kind of like clusters of nests along basically the coast of Rhode Island and then along Monomoy Island. And I think some of the results were kind of sensitive to that. So the fact that, like for piping plovers, there was kind of more impact of adding an additional site seems to suggest that there was more variation between sites, which I think has to do with the fact that common terns tend to gather at shared staging areas after breeding, so the different breeding colonies were probably less dissimilar in common terns, but then also the fact that for piping plovers, you ended up needing kind of a larger sample size to characterize any given site. I think that also had to do with the fact that the sites themselves were not quite as concentrated. So there might not have been as much kind of coordination just because behaviorally they don't coordinate, and also because there was more separation between nests.
Thank you. So the next question is for Andrew and Evan together. Given that the Motus framework and study design tool are being developed to better understand movements and distributions for species like roseate terns, piping plover, and red knot that require Motus technology for this type of data, are there plans to update the SCRAM tool with new data as larger Motus networks are deployed? And how do the limitations of the current Motus network influence the outputs of the current SCRAM model?
Yeah? Okay. Okay, there are a lot of questions there. I might need to ask for a rehash on one of them, but yes, here. So I think SCRAM right now is just taking data from these three species, as was mentioned. I think there's a world where we could start pulling data in from the Motus network in a more live way. That would take some time to get to, but it's entirely feasible to take additional data streams in and turn them into movement models, which gives us our exposure assessment. It would just, there's a lot of steps between the raw Motus data and turning that into an estimate of exposure. So making sure that that process is accurate and can be appropriately streamlined will be the next thing. But I think expansion of species would be a reasonable thing.
Yeah, I think the intention of this project was that it would be updated as new data became available. We're already interested in thinking about not just Motus data, but also some of the GPS tracking studies that are going on now. Still movement information, it's even more precise. So we'd like to be able to incorporate that as well. And I think, the project Evan described, I think those movement models are not for everyone, and it would, if we want to make them more accessible, it's going to take, a bunch of work. That's not to say somebody with the know-how couldn't do these movement models for their own data and make this work once we have it open to accept additional data, which is, we're not that far from that. It's just I was having issues, so we backed away from that initially, but future update will allow custom information. And we also intend population information. That's not set, none of this is set in stone. We're starting from a place, we want to make sure it works. We want the best information to start with, and we'll improve in the future.
There's another part of that question that was, how does the current Motus network influence results? And I think that's pretty interesting. Right now, we sort of don't allow you to estimate exposure in certain areas where we just don't have any Motus towers or we don't have enough detections of the animals. So as we would expand the network, we expand the areas that we get to say that we have information on. So right now it's pretty clear. Though if you try to pick a spot that we don't have any data on, it'll just say, tough luck, we don't have anything. But as we get more and more information, we should be able to eliminate those. And I think in particular, towers offshore would really help because there's a lot more wind energy areas further and further offshore, and we're going to need to make sure we have good estimates of movement out in those areas.
Thank you. So next question is for Rafael. What is the weight and kind of transmitters used in the study, and are they satellite transmitters? And if you're Not quite sure. I can help fill in some of the gaps too.
Yeah, you know better than me, but it's Sunbird low-tech transmitters, 3 grams weight, with solar panels. Yeah. Any other specifications that could be interesting?
Yeah, so in Brazil we use the low-tech Sunbirds. I think base weight's 2 grams, but with waterproofing it bumps it up closer to 3. And they're on the Argos system, so they have locations about 6 times a day if they have full sun. And the accuracy optimally is 250 meters, and that goes up from there. For the study in Maine, we used a similar type of transmitter, but it was the microwave telemetry 2 gram PTTs on the same Argos system. Attachment was for common terns in the Gulf of Maine, we used a harness method. And for roseate terns, we used a glue and suture method that has been used successfully on large sample sizes of tagged roseate terns using nanotags. We did a small pilot study on using a harness with roseate terns on Great Gull Island for satellite tags and had some mortality associated with that attachment, so we're not currently recommending that. And we do have a paper in Waterbirds that describes the details. Next question. This is a Juliet question, I believe. How might a specific project developer determine which population or site to tag in order to best cover use within their project site?
Yeah, that's a good question. That was part of why we kind of did that. I didn't have a lot of time to spend on it, but the analysis looking at the distance of tagging sites from antennas and inclusion probabilities to see if there really was kind of a distance relationship. And it turns out there's not quite so much, at least for the coastal arrays. You do have to kind of go further afield than just the colonies that are really close to the antennas because of the way that birds migrate. And I think the same is true as offshore, even though we don't have as much information. So you're not necessarily looking just at the closest colonies to the site. I think, and you also have to look at, species that don't even breed in the U.S., right, that are occupying sites during winter. So, for example, black-capped petrels are a big deal in sort of the central Atlantic call area, and they only breed in the Caribbean. Northern gannets are a big deal throughout the Atlantic coast, and they only breed in Canada. So I think really it's a species-by-species question, and you have to kind of use the distribution models, like the MDAT models that we already have as a starting point for identifying what species are there, and then looking at what the most likely colonies are that they're coming from, given what we currently know about migratory patterns, both from observation data and from whatever tracking data already exists, using that kind of as a starting point, and then filling in gaps as the information gets better and as we get more movement data and start to pinpoint areas that, that birds might be wintering or breeding that we should be targeting.
Thanks, Juliet. And then there's a follow-up question that I'll address first, and then I can look to others if they have additional input. I anticipate that the current risk tolerance from states and federal agencies may preclude marking 100 piping plover. In addition to being logistically challenging, is Motus the appropriate platform and approach for piping plover? And just some thoughts on that. So for the BOEM-funded study that we did between 2015 and 2017, we deployed 150 Motus tags on piping plovers across multiple sites in southern New England. We did that in very close coordination with our state partners and with the Endangered Species Program at U.S. Fish and Wildlife Service. And we made sure that the tag weight was minimized. So the tags on piping plovers are a gram. And then we also used a very temporary attachment technique, just gluing with super glue to clip feathers in the interscapular region. So we really tried to minimize risk from the tag weight and attachment to minimize adverse effects of tagging. We also did a lot of monitoring post-tag deployment to make sure that there weren't any behavioral changes of tagged adults or impacts to productivity on their chicks that they were raising. That being said, I think it really speaks to the importance of having a robust sample size for these individual-based tracking studies, so you have good population-level inferences from the data, as well as the importance of centralizing data and using data from multiple tagging efforts in combined analyses to really make most of the information from these individually tracked species, especially for ESA-listed species where there's a risk of tagging that needs to be outweighed by the conservation value of the information from that tagging. So I think that's really kind of one of the main themes that we're trying to hit on this symposium, and something that could be coordinated more closely through groups like the RWSC moving forward. Any other comments around that? On to the next question for Evan. How do you handle Motus systems with adjacent wind farms? Do you try to combine efforts? If so, how do you coordinate with each developer?
That's a good question. I think it, again, goes back to what question you're asking. If you want to know something about use specifically in one area, you might get some strong value from coordinating with partners and adjacent bodies. How you do that, I think, is going to be something we are working on in the coming years. I think to some degree RWSC and groups like that provide excellent opportunities for us to coordinate research efforts, and projects like Project WOW, where we have a lot of coordination across a lot of developer stakeholders, give us a lot of opportunities to make those connections and help leverage data sets. We also need to work on making data available, working together. I mean, there's a lot of engagement and sort of coordination that would need to be done. But I mean, while we didn't look at this in the modeling, generally more stations are better than fewer stations. And I think it's definitely an interesting opportunity, particularly as we start asking questions. If we start trying to figure out if Motus can really help inform questions about displacement and how animals are moving and changing their behaviors, we're gonna need a fair number of stations to get good estimates on those positions. So it's definitely something we're looking toward, and it's definitely one of the reasons why we've worked so hard to create guidance with a lot of developer partners over the past couple years. So we've been trying to pull people into that process in a very open and clear way. So you know, I think we're still working on exactly what strategies we want to use moving forward, but more or less we're happy to help try to coordinate communication. If you're interested in kind of collaborating across partnerships, we're happy to try to make that happen. So.
Thanks, Evan. Next question for Rafael. What is the wintering population of roseate terns at your monitoring area, and how does that compare to wintering populations elsewhere?
Yeah. Okay. We have a lot of gaps yet in Brazil about what the birds and where they are. Yeah, a lot of gaps. So what we know already, the most part of these birds are from the northeastern US population, especially from Great Gull Island and New York and Massachusetts. So, but we know that because the banded birds. However, we have a lot of unbanded birds that we find. So just to summarize, the number of collided birds since 2010 until now is 344 collided terns. So between roseate terns and common terns, the large numbers from roseate terns. So we have about 42 birds that we found banded from New York and Massachusetts, and we have more than 300 that we don't know from they are. So we are running, by now we are in a collaboration research with the Smithsonian Institute to run some genetic analysis to discover if these birds are from other population as Caribbean population that we don't know a lot about it.
Thanks, Rafael. And I just want to acknowledge the amazing work that Rafael and his collaborators down in Brazil are doing to identify, monitor, and minimize collisions between roseate terns and power lines in the northeast region of Brazil. It's really an incredible project with lots of partners internationally, and yeah, excited to be part of it and help keep it going. along the collision theme, here is a question for Andrew. Approximately how much Motus data do you think is necessary for a species or facility for the SCRAM, CRM to be usable?
That actually might be an Evan question, but we haven't looked at that yet. I think we basically used all of the data that Pam had, but there's clearly gaps in that data. As Evan mentioned, we have not only spatial coverage gaps because with piping plovers they weren't tagged north of Cape Cod, so any southbound flights would have been missed, so we can't understand movement and densities offshore, say in the Gulf of Maine. There are also no offshore towers, so we know there's spatial gaps. We may be missing birds that didn't get picked up until later, or if they lost tag after or before the tag ended, we could miss that offshore movement. So, you know, more is always better. Numerically, I think we would definitely have to look at that. It's a good question. It's something I think we probably should look at in depth at some point.
Yeah, besides continuing to say we don't know, I think there's two things that you need to think about when you're running a multi-state movement model like we're running for SCRAM. You need to be thinking about the total number of birds you have tagged, so along the lines of what Juliet was doing, and thinking about how many animals are tagged and what kind of coverage you're getting. So we need to sample a wide enough population of animals such that we feel like it's representative of a wide enough number of animals such that it's representative of the population. But on the other end, we need just like actual strings of data where we have positions of animals that we can feed into a movement model. We have to estimate, in a multi-state model, we have to estimate parameters about bearing and flight speed and a variety of things, and then the transition probabilities between those states. And so we need a sampling of movements along time that allows us to do that. So while we haven't done a sensitivity analysis specifically to try to ask that question of how long those strands have to be, I'd say the models we do have are working pretty well, but there is a fair amount of data on those species. So.
Yeah, thanks, Evan and Andrew. So the next question is for Juliet. Did you vary the resources for the terns, parentheses, I assume no, over years? Well detections may stabilize after 2 years. The shifting resource base would seem to point to the importance of multi-year work.
Yeah, I would say, so this was just resampling existing data, so I didn't vary anything. Like the interannual variability just came from the underlying data. That said, we did see improvements in inclusion for each year that we included, up to 3 years, and that was what the data limited us to. So I would say there is evidence that adding years also adds information. It was just that when you did a trade-off between adding sites or adding years, adding sites added more information if you have the same number of tags distributed over multiple sites compared to multiple years. So that kind of shows maybe that within sites, birds are pretty stable in terms of their year-to-year behavior, and we do know that with aquatic birds, they tend to be pretty consistent in their behavior. So that makes sense. I think thinking about longer-term shifts in baselines over years, it does make sense to think about sort of long-term deployments and how to best resource that. That might be maybe not deploying every year, but deploying every 2 years or every 3 years to try to get that kind of longer time series. But I definitely wouldn't minimize the importance of interannual studies. It's just when you're doing kind of a cost-benefit analysis of the trade-offs, like having multiple sites is probably the first consideration, and then trying to maximize the temporal coverage as well.
Excellent, thank you. A couple of questions for Rafael. Kudos, you speak excellent English. And excellent presentation. What software did you use for the maps?
Okay. Yeah, it's just Google Earth. There you have a specific tool, name it Google Earth Studio. Then you can do some videos with KMZ files. So you just put some shapes there, and you can record animations. Yeah.
Thanks, and here's another question. Is the Brazilian government aware of the potential impact of offshore wind?
Yes, it's the simple answer for that question. But no, it's also an answer for that question because we have environmental federal agents that are real enrolled in the problem. It's they are following what we are doing together with the United States. We are using the data to try to improve the status of the birds. We just launched a new list of endangered birds. However, between the environmental agency states, the environmental agents and the executive power in Brazil, we have some borders that are kind of hard to cross, especially, yeah, we should, I don't know if it's the better environment to talk about politics here, but the environmental agents that regulate this sector already know and they have concerns about it, and we are doing the better that we can to put this in an executive way to the regulators do something about with that.
Thanks. Perhaps another type of hard question. This one's for Evan. Is there strong evidence that seabird and shorebird flight heights are unaffected by offshore wind infrastructure? That is, are flight heights anticipated to be similar before or after turbines are installed, assuming the birds are flying through the array and not avoiding the facility altogether?
Yeah, that's a good question. I mean, essentially, we have to assume that before they're up, right? We just have to measure flight heights the best we can and see if that's going to correlate into exposure. In terms of how much we see it change, it's actually kind of challenging because avoidance exists. They can avoid in all three dimensions, and so we do know because there's not a pile of there doesn't seem to be a large number of collisions that they are avoiding, and they could be avoiding in many directions. And many of the species that are flying at heights that would be exposing them to offshore wind have pretty high avoidance rates, like northern gannets, and so. We actually kind of lack data to test some of these things. Though I think it's very possible that it does, particularly if you think about attraction in migratory animals. If there's strong lighting in some of these areas, we know that migrant birds are attracted to those situations. So it would not be surprising to see the flight heights actually change, though I think different kinds of studies are needed for that. Bats as well. We didn't talk about bats much, but Motus could definitely be useful there. So I think it's reasonable to assume that attraction is going to occur in many of these species, and it's something we need to be planning for because I don't think all pre-construction flight heights are going to be accurate moving forward. But for now, it's the best we got, but then we need to do some behavioral studies to validate.
Excellent point. Thanks, Evan. And with that, we're at the end of our questions, and we're right at the top of the hour. So I'd like to thank everybody for joining and participating today, and thanks again to all the speakers for the excellent talks.